Apologies for the non-Newtonian blunder in class. I'm going to redo this discussion here on this video. So what we discussed were first non-Newtonian fluid. Again, assume we have this rheometer where we impose a certain velocity on the top. So we impose a shear rate by moving the top surface, and we have a linear shear. So we have a quiet flow in the gap, and we measure the shear stress. If we increase the rate of shear strain, and we find that the shear stress which we measure linearly increases, then we have what is called a Newtonian fluid. We have a Newtonian fluid, and as you see, this slope will correspond to the viscosity. So the slope corresponds to the dynamic viscosity. This is when the shear is linear, the shear stress is linear in the rate of shear strain. Now, non-Newtonian fluid, a way of describing those non-Newtonian fluid, a general framework, would be to say, well, instead of being linear in the rate of shear strain, the shear stress is going to be a power law of the rate of shear strain. So let's say that the shear stress is equal to a constant times the rate of shear strain at a certain power. And let me call n this certain power. In that case, let's assume first that n is strictly bigger than 1. So what would the curve give us? If n is strictly bigger than 1, then the curve we get, think about n equals to 2, for instance, it looks like a parabola. So we get a curve like this. Now if you remember, if you see the slope of this curve roughly as the viscosity, then you see that as you increase the rate of shear strain, the fluid becomes more and more viscous. The slope here increases. So in our QUET experiment, the higher the shear rate we impose, so the higher the velocity on the top plate we impose, all of a sudden the shear stress becomes non-linear, increases non-linearly. So it looks like the viscosity itself is increasing. So that would be a shear thickening fluid. So when n is strictly positive, we have a shear thickening fluid. Now the other case would be if n is smaller than 1. In this case, think about n equals to 1/2, for instance. In this case, we will get a curve which looks like this. So this here is shear thickening. In this case, as we increase the rate of shear strain, so as this velocity of the top plate in our rheometer is increased and we're trying to shear our flow faster, the shear stress still increases, but it seems to increase less. So it looks like the viscosity is decreasing as we increase the shear rate, the rate of shear. So that would be a shear thinning fluid. So when n is strictly negative, smaller than 1, we have a shear thinning fluid. So here, that would be shear thinning. So up to this point, everything went well in the lecture, except that then I wanted to give the example of a fluid that has a yield stress, so ketchup, for example. And because ketchup is thick, I had in my mind it was shear thickening, so I inverted everything. But actually, a fluid with a yield stress is a shear thinning fluid. So ketchup is, on this top graph here, a fluid with a yield stress would look somewhat like that, what you would measure. It's also called a Bingham fluid, or fluid with a yield stress or yield stress fluid. And what you have is indeed, if you want to the fluid to flow, so if you want to have a non-zero rate of shear strain, you need to impose a certain amount of shear stress, otherwise it doesn't flow. And then if you apply here more shear stress, then all of a sudden it starts to flow. So this is a very shin thinning behavior. And so ketchup, but a lot of other products like mayonnaise or everything which you spread are shear thinning fluids. So let me give you an example here. So Bingham fluids, that's it. That means yield stress fluids. For example, ketchup, mayonnaise are all shear thinning fluids.